In this class, we will discuss equalizers, which are used at the receiver to cancel the effect of channel and ISI introduced by the channel. To motivate the use of equalizers, first let us recall what we have done so far. We have discussed digital modulation techniques, where at the receiver we have assumed that the consecutive symbols do not interfere with each other, and we have also derived the condition for no intersymbol interference. We will just revise what we did, and from there we will start the new topic on equalizers. So, if we use a transmit pulse GT, GT is either the baseband pulse or the passband pulse, and once it goes through the channel with the impulse response HT channel filter, and of course, there is noise, and then at the receiver we implement some matched filter receiver. Now, this is the, let us say this is the baseband pulse, and there is the receive filter at the output of which we sample every t seconds. So, this is sampled at multiples of capital T seconds. Now, we are transmitting not only GT, but shifted versions of GT after multiplying by the information carrying values. So, what we are transmitting is actually summation some information carrying values, then G t minus n t. But when this signal goes through the channel and then it goes through the receive filter, what we receive is summation I n, then x t minus n t, where x t is now this plus, of course, there is some the noise also goes through the filter receive filter, and at the output of the sampler you have some noise, but the signal here is this plus some noise signal. And what is x t? X t is the convolution of G t, H t and the receive filter R t. So, when we sample this signal every capital T seconds, we will get not only at the n t second, that is at the nth sample, we will not only get I n, we may also get some contribution of the other symbols if the x t is not chosen properly, that is if G t and R t are not chosen properly to have x t satisfying certain conditions. So, we have seen that for ISI free reception, we need this to be 1 only for k equal to 0 and 0 otherwise. So, that all the shifted pulses, the x t is the pulse resulting from G t, H t and R t, and after G t goes through all these filters it becomes x t here, and x t should have 0 values at the multiples of t seconds except at the 0 itself, because at let us say small t equal to capital T, the next sample is taken here and that sample should be contributed by only the next symbol. The previous symbol should not contribute anything to that sample, and from there comes the restriction that t equal to capital T, at t equal to capital T the value of x should be 0, and similarly at all other times multiple of capital T. So, this is called the Nyquist criteria, and we have discussed already this criteria before in depth, and we have seen what it means in the frequency domain also. Now, it may not be always possible to enforce this criteria in practice for various reasons. So, one such reason is that the channel itself may change with time, and as a result it may be difficult to adaptively design GT based on what the channel is. So, if the channel changes slowly or fast with time, the GT for ISI free transmission needs to change with time, and that requires difficult dynamic design of the pulse GT. So, that involves first of all the channel needs to be estimated at the receiver well, and then that information needs to be transmitted back to the transmitter, and the transmitter needs to design GT and use that GT for transmission, and that is a difficult thing to do in general. So, often what is done is, if the channel is changing with time, you may not consider channel, you simply consider RT and design GT accordingly and work with some suboptimal system. It may not be exactly ISI free. Then we would try to remove the ISI in other manners, which we will discuss in this class. Okay. So, let us first formulate what will happen if we do not have ISI free transmission. What is the exact form of ISI at the receiver? If we transmit summation I n g t minus n t, n equal to minus infinity to infinity, if this is transmitted through H t, then it goes through R t. We are not drawing the noise here, but noise is there. We are not considering what will happen to the noise at this moment. So, here what we have is summation I n x t minus n t, and then we have sampling. So, these samples, let us call them x, let us call them y k, the kth sample is y k. Then what is y k? Y k is this signal sampled at k t. So, that will be summation n equal to 0 to n equal to minus infinity to infinity and I n x k minus n, where this is nothing but, so x l is nothing but x sampled at LTth time, LT seconds. So, this is what we will have at the output of the sampler. This has contribution from all the symbols, and ideally we would like to have only I naught some non-zero value, and all the other components here should be 0. So, that the 0th symbol is not interfered by the other symbols which came before or which will come after the 0th symbol. So, this is basically I 0 x k plus n not equal to 0 I n x k minus n. So, this is the ISI part. Okay. So, this actually y k will be this plus noise. And this actually looks like, this formula looks like as if x k, the discrete time signal x k is going through a filter, and this is the convolution. So, the equivalent model for this whole system, this from here, if you consider I n being fed and after modulation it is going through h t, r t and then sampling, then the discrete time signal we are getting here looks like convolution of the sequence I n with some other discrete time filter impulse response. And so, the equivalent model of the system becomes I n, and there is a discrete time filter with impulse response x k, and there is some noise, discrete noise. And here we have y k. And our job at the receiver will be to cancel the effect of this filtering and recover what was transmitted. So, ideally we would like x k to be 1 only for k equal to 0 and 0 otherwise. That means, the discrete time filter should have delta as the impulse response, but it may not be possible to have such an impulse response here, because that will be difficult to design, because GT will be required to satisfy some conditions depending on the present state of the channel, and the design of GT may not be so easy to do satisfying this condition. So, after having this, even if we have some non-ideal filter here having some arbitrary impulse response, how to get this I n sequence back from y k is what we would like to investigate. So, what do we do from this is that we in general we call a system through which this y k will be passed at the receiver. So, this is what we are considering now is called linear equalizer, where the way we try to recover I n from y k is by passing y k through a discrete time filter. So, it does some linear operation on y k, it combines some y k's by the impulse response of the filter by doing convolution. So, after passing y k through the filter, and let us say this filter has impulse response non-zero c k from the range minus k to k. And then suppose we receive here I k hat, we want this I k hat to be same as I n, but it may not always be possible. What may happen is that there may be still some ISI remaining, or there will be certainly the noise added to this, some function of the noise which is the noise itself, so some different noise, and this I k is nothing but j equal to minus k to k C j y k minus j plus noise. And what is done after this is passed through the quantizer, basically the detector for the constellation. So, what does this quantizer do? This is an estimate of the value transmitted, the value transmitted in I n, the value of I n is an estimate of that, but I n was actually a value picked from a constellation. It may be, if it is a real value, it will be possibly from a PAM constellation, or if it is complex valued, it may be a 2-dimensional constellation from where it was chosen. So, the quantizer will pick the nearest constellation point from I k. So, if you had 16 QM constellation, if it was a complex constellation, this I k hat may be a point somewhere here, and this quantizer will choose the nearest point. It will quantize to the nearest constellation point. That is what the quantizer does. And this is the estimated symbols. These are the estimated information symbols. Now, the question is how to design this system. This is the equalizer. This is the linear equalizer, and we want to design this system, and how to do this. So, there are different ways of designing this system depending on what criteria you impose on these symbols. What is the criteria for the performance of this equalizer? When do you say that one equalizer is better than another? So, based on that criteria, we have to design this equalizer. And there are very standard two techniques, two criterias used very much in practice. One is called the peak distortion criteria. Peak distortion criterion, and what it tries to do is to minimize the worst case error, that is the absolute value of I k minus I k hat. So, we will not consider the noise part, because noise is random. We will not bring that in this criterion. What we say is that this is the estimate of the transmitted symbol I n, I k, and we would like to see what is the maximum difference I k hat and I k can have. That will depend on C k, and we would like to design C k so that maximum difference between I k and I k hat is minimized. So, it will be maximum I k hat minus I k for a given selection of the equalizer will be maximum for a certain choice of the symbols, input symbols I n, that is I 0, I 1, I 2 and so on. So, this sequence, when this sequence has a certain value, then this I k hat minus I k will be maximized, and that worst case difference we want to minimize. So, that is the peak distortion criteria. So, this we want to minimize this in absence of noise. So, what is the solution we reach if we take this criterion? If we take this criterion, it can be shown that the optimum solution for the equalizer filter which minimizes this quantity is that filter whose Z transform is the inverse of the equivalent channel filter. That is, we have seen that this yk depends on in in a way which is equivalent to passing in through a filter, discrete time filter xk, and this impulse response xk has a Z transform, and that is the Z transform of the impulse response, from which you can get frequency domain characterization of the filter, frequency response of the filter, and what we want to take here is the inverse of this filter, that is 1 by xz. Xz is the Z transform of xk, and Cz, which is the Z transform of Ck, will be chosen so that it is 1 by xz. And this is also intuitively a good selection, good choice for the equalizer filter, because what it is saying is that what it is trying to do is to invert this filter. Here we are putting a filter, we are passing yk through a filter which is inverse of this filter, so that we get back this sequence in at the output, except for the noise. This noise also will go through the same filter, and at the output of it there will be some other sequence of noise. And at least the signal part will be recovered fully. There will not be any intersymbol interference left between the output samples. So, that is the inverse filter solution for the linear equalizer. And though this completely removes ISI, it has one drawback. The drawback is that it amplifies noise. It amplifies noise in some bands wherever this discrete time filter has very high attenuation. So, if we consider the frequency response of the discrete time filter xt, xk, that is, if you consider the frequency response of this filter xz, then if it has, let us say, some very high attenuation here, then the Cz will have very high gain in this frequency, because it is just the inverse filter of this filter. So, it will have something like this, and as a result the noise which is introduced here and which is going through that equalizer filter will be amplified very much in this part, wherever this filter xz has very high attenuation. And that amplification, too much amplification of the noise in some bands actually creates problem, because the overall noise itself increases because of that. So, it amplifies noise, otherwise it cancels ISR completely. So, the contribution of neighboring symbols. So, if you plot I naught here, this is I naught, this is let us say I 1 and so on, at the output of it you get this plus some noise. There is no contribution of I naught in I 1 hat. So, if you estimate this I naught I 1 hat, there is no contribution of I naught on I 1 hat and vice versa. So, there is zero interference from the neighboring symbols. This is referred as zero forcing. So, that is why this equalizer is also sometimes referred as zero forcing equalizer, which means that by this equalizer there is 0 intersymbol interference. Okay. So, it completely eliminates interference between neighboring symbols, but it has the drawback that it amplifies noise in high attenuation frequencies, at the frequencies where the xz has high attenuation. Now, another criteria which is also very commonly used is the MSE criteria, that is minimum mean square error criteria. What this says is that instead of neglecting noise while designing the equalizer filter, which we did in this case, if you remember, we actually did not consider noise at all while designing the system. We said we want to minimize the worst case error in absence of noise. So, we did not consider noise at all, and that ultimately resulted in a solution which amplifies noise too much in some bands. So, if we want to avoid the problem, we actually need to consider noise as well as interference together and design an optimum system. So, what criteria should we take for that? A very simple criteria is minimum mean square error criteria, which says that if this is the error for the kth symbol, that is ik minus ik hat is ek. In the peak distortion criteria, we wanted to minimize the absolute value of this, maximum absolute value of ek. But now we want to minimize the mean square error, which is the expected value of ek square. So, this is the square error, squared error, ek mod ek square is the squared error, and because this is no more random, this is no more deterministic, there is some noise, we have to take expectation of this, and we want to minimize this error, which is nothing but ik minus ik hat square. So, this is the mean square error, and we want to minimize this quantity. And the solution which comes if we want to minimize this quantity while designing the equalizer filter is a slight variation of the zero forcing equalizer. It is given by 1 by xz plus n naught, where n naught is the n naught by 2 is the variance of noise, the discrete time noise, or equivalently n naught by 2 is the power spectral density. Okay. So, this is the filter which minimizes the mean square error between the transmitted symbols and the received symbols. Now, both these filters are a single linear filter. Both these equalizers, they are basically a single linear equalizer which is designed based on different criteria. One is designed by taking peak distortion criteria, the other is designed by taking the mean square error criteria, and we get two different solutions if we design based on two different criteria. But this is not the only way one can design an equalizer itself. Another equalizer which is very commonly used, another structure that is commonly used is decision feedback equalizer. So, what is the philosophy of this? The philosophy of this is that when we considered a linear equalizer here, after we have received some symbols here, and we have also decided after quantization what was transmitted from the constellation point, then even though there is some interference here from those symbols which we have already received, we are not using these received values, these values which we have already detected here, to cancel the interference from the future symbols which are coming by these points. So, in other words, when we have received here, we have already decided the values for I naught, I 1, I 2, and suppose we are receiving the future symbols here. The interference caused by I naught, I 1, I 2 is known to us, because we probably have estimated this x k, this filter. So, we will be able to determine what is the contribution of I naught, I 1, I 2 on y k for the future symbols, and then we can cancel the effect of I naught, I 1, I 2 from the future values of the samples that we are passing to this equalizer, and as a result we will be getting a better estimate of these symbols, these INs here itself. And so, possibly we will need a smaller length filter, because this k itself is also a parameter which determines the complexity of the equalizer. We would like to have as small capital K as possible. So, if we cancel the effect of previously detected symbols from the incoming signal, then it may be possible to equalize this stream with a smaller length filter here, whose job will be now to cancel the effect of future symbols from the past symbols only. So, which is basically not really the effect of future symbols on the past symbols, but which is taking help of the future symbols to detect the previous symbols, because the previous symbols will have some effect on the future symbols. So, future symbols also carry some information about the previous symbols. So, we can still use a filter here even after cancelling the effect of previous symbols from the future samples. We can still use a filter here, so that we can cancel the effect of future symbols, cancel the we can use the information that is available in the future symbols to get a better estimate of the previous symbols. So, we will have two filters. One is the feed forward filter, which is the forward filter. So, this is and then we will have, of course, this detector, symbol by symbol detector, and then we will have we will have the estimates of the symbols I k, the information symbols. After getting these values, what we said is that now the samples we are receiving here have some effect of these symbols which we have already detected. So, we will derive the effect of this on this signal, and that means which is basically saying that we will pass this I k hat through the filter x k itself, because this I n sequence actually passed through x k to give us this stream, this signal. So, we will pass, after detecting I n, we will pass it through the same filter and cancel it from the received signal. So, how to design this filter exactly, how to design these filters, this filter also exactly we will consider now. But what we want to put here is that the fundamental structure of the equalizer is that from this signal we will pass it through a filter and then subtract it from this signal. So, we are receiving yk here, we are passing it through a forward filter, but at the end of it we are also removing the effect from the previously detected samples. So, we will design these two filters together, so that the error here is minimized. That is, we get ik hat which are almost same as ik. So, what is the ik hat here? Ik hat is j equal to minus k1 to 0 Cj So, if you consider the signal here, this is the quantization is also happening here, but we will not consider that. We will take this signal is sum of two signals, this is negative, but you can say that this filtered impulse response itself is negated, so that this is plus itself. So, this becomes C j prime I tilde k minus j. So, this is, we can assume that this is going through this and this is yk minus j, and this is passing through this. So, the two filter outputs are taken and they are added to get ik hat. Now, again how to design these two filters is the question, and again we can have two different criteria for designing the filters. One is peak distortion criteria, which will give us one solution, and another is MSE criteria, mean square error criterion, which will give us yet another solution. So, what we are saying is that we will have these two filters where the previous decisions are fed back to the decision process of the future symbols, and there is the forward filter as before, but hopefully we will need a smaller length filter here, because we have cancelled the previously detected symbols from the future symbols. So, there is less ISI in the signal, because there is some more cancellation going on even after this. So, we can afford to leave some ISI here, which will be cancelled by this contribution. So, this is the decision feedback. This is the previous decisions are fed back to the decision process of the future symbols. That is why this filter is called the decision feedback equalizer. Now, as we said, these two filters now need to be designed based on some criterion, and just like feed forward filter, we have two different criteria in this case also. One is peak distortion criteria, the other is MSE criteria, that is mean square error criterion. And by these two different criterions, we will get two different solutions for the two filters. Now, these are some techniques for equalizer design. There are many other techniques and there are many other variations of the same ideas, which we will not discuss in this course. There is also another important concept, and that is to design the filters adaptively. So, as we said, the channel in real life may actually change with time, and we as a result may like to design the filters adaptively. As the channel changes, we like to change our equalizer filter also. So, there comes the adaptive equalization. And adaptive equalization we will not discuss in detail, but we would like to just mention that there is something called adaptive equalizer. And again we can have different criteria for designing adaptive equalizers. Different criteria will give us different types of solutions, and there are various ways of designing adaptive equalizers. Some are more complex than others, some use one criteria, some use another, and so on. And there is altogether a different approach to estimating the transmitted information stream than designing equalizers and trying to cancel the equalizers. So, the whole problem itself can be formulated as that of a sequence estimation. So, what is that? As you said, we have a sequence I n that is equivalently passed through a linear filter x k. Then there is some noise. What if we know this filter and we know the characteristics of the noise and we know what we receive? Of course, that we will always know. We are receiving this sequence and we want to estimate I n from y k. That is the original problem. And in the equalizer design, we have considered a simple structure for the processing we do after this, and that is, we said we will either use a linear filter here and then do quantization, or we will have a decision feedback equalizer, which is again done by implementing two filters. One is forward filter, another is feedback filter. But we have not addressed the problem with its originality, and that is, we want to estimate I n from I k, and we want to first say what is the criterion for estimating. When do you say some estimator is better than another way of estimating? And one can say one very useful criteria is ML estimation, which we have used for symbol by symbol detection for ISI free transmission. When there is no ISI, when we do symbol by symbol detection, we have used ML estimation. For Gaussian noise case, we have seen that that is equivalent to picking up the constellation point which is nearest to the received signal. That can also be, the similar formulation can also be set up for sequence estimation. We want to basically choose a sequence I n after we have received a sequence y k, that is y naught, y 1, y 2 and so on. We would like to choose that I n, that sequence of I n which is most likely. So, we can compute the probability for which this receiving this is most likely. That means, compute the density function conditional density probability density function of y naught, y 1. Let us say we receive till capital N may be 1000, maybe 1,000,000, very large, very long sequence. We observe a long sequence and then ask the question, for what sequence of transmitted symbols, that is I naught, I 1, I n, for what sequence of transmitted symbols this density function value is maximum. So, for what transmitted sequence, this is the probability of this, not really probability, but probability density at this value of the sequence is maximum. That is the maximum likelihood estimation we know, because originally we in another context of detecting symbols, we said that we are transmitting one random variable x and we are receiving one random variable y. Maximum likelihood estimate of x is the value of x which maximizes f y given x, the density of x given y given x evaluated at the received value. So, we want to maximize this, that is the maximum likelihood estimate. So, that same concept is used here in terms of sequence. We have, say, we transmitted one n length sequence and we have received one n length sequence, and we want to have the ML estimate of the transmitted sequence from the received sequence. So, we are saying our ML estimate is that transmitted sequence for which the density function, conditional density function of this sequence given that transmitted sequence is maximum. That is the maximum likelihood estimate. And in general, it is very difficult to perform this ML estimate, because this is a very high dimensional problem. If you, let us say, we are possibly transmitting hours after hours, hour after hour, and as a result we will, this capital N will be very large. So, how do we do this? This is too complicated a function, there are so many variables, say 1 million or 10 to the power 100 variables. So, how do we choose that so many variables from a very long sequence? And also, can we wait to receive all 1 million symbols before we decide even the first symbol? That is what this says we should do. We should receive all the n symbols and then only we can decide all these together, including I naught. So, to decide what was transmitted at the 0th symbol interval, we need to wait for all these n symbols to be received, and that is too much delay to be afforded in practice. But it can be shown that there are iterative ways of doing this. So, in other words, you will not need to wait to receive all the capital N symbols to decide on even the first symbol. So, there is iterative ways of doing it. So, where after receiving 100 symbols, you will be able to estimate, let us say, 5 symbols, 5 transmitted symbols. Then after receiving 150, you will be able to decide about 50 symbols. So, there will be some lag, there will be some fixed delay, but you will be able to estimate more and more symbols as you receive more and more. You do not have to wait to receive the whole block of symbols before you decide even the first symbol. So, the famous algorithm which can be used to do that is called the Viterbi algorithm. For ML sequence estimation. If you want to know more about Viterbi algorithm for ML sequence estimation, please look at the book by Prokis. Reference is Prokis Digital Communication. And this Viterbi algorithm, the same concept is not only useful here, but it is also useful in decoding of a family of codes called convolutional codes. It can also be used for block codes, but it is especially famous for convolutional codes, where basically something like convolution happens, something which is happening here in the channel and the whole system, equivalent system. there are coding methods where you pass the bits, the digital signal through a digital filter at the encoder at the transmitter, and you then transmit, and after receiving the sequence, you can estimate the transmitted sequence by using Viterbi algorithm. The problem, because the problem is again same, you have some transmitted sequence which is passed through a filter, and you receive the sequence and you want to do ML estimation of the transmitted sequence from the received sequence. So, again you do not want to wait for very long time before you even detect the first symbol. So, there needs to there is requirement for an algorithm which can give you an estimate of the first symbol after receiving a reasonably good number of symbols, and then as you receive more and more bits, you would like to estimate more and more transmitted bits. So, there again Viterbi algorithm is used. So, that class of codes are called convolutional codes. So, we have discussed in this class equalizers, linear equalizers, we considered feed forward equalizers and decision feedback equalizer, commonly abbreviated as DFE, and in each case we have considered two criteria for designing the equalizers. One is peak distortion criteria and the other is MAC criteria. And then we have mentioned briefly about first adaptive equalization, where you adaptively change the equalizer based on the way the channel is changing. So, that is adaptive equalizer. And third, altogether a different approach for estimating the input sequence from the output sequence by according to an overall criterion, and ML criterion is so popular. ML criterion based sequence estimation. And one very popular method for this is Viterbi algorithm. Not only this Viterbi algorithm, for any of the topics please refer to ProKids Digital Communication. Thank you.